아니에요.
What?
수업 시간에 원인데.
Okay, let's continue.
Where's it?
So,
Get out.
let's look at this example here. Alright, straight line graphs. So when we directly generate a linear fit, then what's next, right? So when it occurs, then we should focus on the gradients and intercepts. Gradients and intercepts can be determined and related to the relevant physics theory in the conclusion. So whenever you have a linear graph, it is always a meaningful steps to try to discuss if the gradient of the graph or the intercept of the graph or even the area of the graph represents any physical quantities or does it have any physical meanings behind it. Okay? Always think about those three special things, especially gradients and intercepts in physics. A non-zero intercept sometimes may suggest a systematic error, okay? Because you're constantly above the line or below the line, so non-zero could mean suggest a systematic error. Or it may relate to a physical quantity. If it's not a systematic error, then it could represent some physical quantity, maybe a constant, maybe it also depends on your IA or your experiments context, okay? Different models could explain different stuff. So in the cases where a best fit curve has been drawn, the student must decide if the data can be linearized easily. What does linearize mean here?
Straight line.
To straighten it, right? So you have a curved line, but you don't want it to be curved. You want it to be straight. So you make it straight. But you can't just directly make it straight. You need to have some mathematical algorithm transformation to make it straight. Okay? So, relevant background theories, for example, squaring reciprocal of one of the variables or dimensional analysis can provide directions or even use logarithm. You guys have learned log already, right? Logarithm in grade 10? Okay, so in physics, it's possible that you're constantly going to use the tool of logarithm, okay? Can provide direction. Although this normally requires ideal data, it should be noted that the linearization of data can be a useful exercise, but is time consuming and may not be worth pursuing at the expense of other tasks. Even though it says that, but honestly, if you want to get a great score in IA, do it. Linearization is a plus, okay? So, for instance, consider the data from the previous example. Oh, sorry. Previous example, which is this one here, right? This one, we finally determined that it's going to be a best fit curve, this example here. How can we linearize it? So, we have independent and dependent variable here. Let's see how did it linearize it. So we take the reciprocal of one of the variable, which is we take the reciprocal of the dependent variable, independent variable. And these data are then plotted. So you get this here as well, right? Now you see it kind of fits like a straight pattern now, with y is the 1 over independent variable. Y-axis is the reciprocal of the independent variable. So then you get a graph that is almost linearized. But notice that doing those extra operation, for example, to take the reciprocal of the independent variable, could to some extent change the size of your absolute uncertainty. You see? So Does that mean that those data points does not have absolute uncertainty? No. Then why there's none? Error bar. Why? Why there's no error bars for those data points? What could be the reason? Too small to be seen. After the operation of 1 divided by independent variable, those data points uncertainty is too small to be drawn on the graph. But it does not mean that they don't have uncertainty. Are we clear? Okay. So in that sense, when you draw the best fit line, it means those 3 points, basically you have to pass through them because they have small uncertainty in this case. All right. So that's the first way. We can take reciprocal to linearize something. Right? It depends on your data points. It depends on, you can try. You don't know, you can try. Okay, you can try different methods. So the second way, an alternative approach is to plot the logarithm of the dependent variable versus the independent variable. So we still keep the independent variable as like that, but the y-axis, we log the dependent variable and put it onto our y-axis. That's the second way to linearize it. And then you see still the first 2 data points, the error bar is too small to be seen in the graph. Okay? Any questions for me? Okay. Let's move. All right. So that is linearization. So when you don't understand why do we need to linearize, what's the point? The area where students struggle is linearizing the data, and linearizing a graph means to adjust the variables so that a curved graph can turn into a straight line graph. This does not mean to fit the curved data points with a straight line, like you do no transformation, you directly just put a line. That's a pretty bad thing. That's not linearization. That's a bad fit. It means to modify one of the variables in some manner using some algorithm or operation such that when the data are graphed using the new data set, the resulting data points will appear to line in a straight line. That's what linearization actually means. Then why do we need to linearize it? What's the point? A linear best fit to the data can give information from the slope and intercept open to the physical interpretation for the students who are not in calculus. For math A.0 students, do you already learn calculus? What about SL? Do we have any SL students here? Oh, all of you are A.0? Did you guys learn calculus in physics SL? Pardon me? Just a bit, but not gonna be deep. So that's the reason why in physics here we introduce you linearization, so that even if you guys don't learn calculus, we can still do some physical analysis, try to interpret the meaning of the slope and the intercepts here, okay? Because if it's curved line, then yeah, if it's curved line, then you probably just gotta use calculus. So that's the point. That's the meaning. We encourage you. We also like stuff to be straight because it's easier to analyze. So we encourage you to linearize them. Do we want to do some practice example for this? Let me see if there's anything else to talk about later. Join the graph. Okay, we might have some time to do some practice, so sure. Okay, let's look at this example problem. The time period of t of oscillation of a mass, which you're going to learn in simple harmonic motion, of a mass m suspended from a vertical spring is given by the expression period equal to 2 pi square root m over k, where k is a constant. Which one of the following will give rise to a straight line graph? Okay, why? How?
Because you have
It's a direct relationship.
So
No, exponential.
we know this relationship, right? Currently, this is constant, so we don't care. K is constant, we don't care. So basically, the relationship, if we use y represent t, it is basically y equal to root x, right? So then we know that if we directly plot y over x, it's gonna give you something like that, right? It's not gonna be a linear line. So how are we gonna make it linear? We can square it, right? So square both terms, we're gonna get y squared equal to something times x. So y squared is t squared, x is n. So t squared against n, we choose A. Clear? Very good. Number 2.
D.
D. Do we need to explain it? No? Okay? No? Or yes? It's okay, it's okay. I encourage you
4
guys.
pi square is a constant. So
Yeah.
Yeah.
4 pi is 4 pi squared is a constant. So if you take A as y, and then you take 1 over t squared as x, then this can be rewritten as y equal to 4 pi squared times x, where basically x is 1 over t squared. So 1 over t squared is your x, A is your y. Make sense? Okay. More examples. Okay, so those examples you can look by yourself. Okay, here, drawing the graph, some details we might wanted to look at together. So when we draw the graph, in many cases, the best way to present an analysis data is to make a graph, right? And a wonderful tool of communication. So when making graphs, we have 10 details to look at. Number 1, the independent variable is always on the x-axis, and the dependent variable is on the y-axis. We're all good with this one, right? Number 2, every graph should have a title, that this concise but descriptive. Okay, so not too long, but it should have the key information included in your title, in the form of graph of your dependent variable versus your independent variable. Number 3, the scales of axis should suit the data range. That means you should pick, you don't want, for example, you don't want to have a scale that your graph is, your data points is only have like that. Or you don't want a scale of your graph like that, right? That's what it means. You should have a proper size of scale like that. Does that make sense? Okay. So number 4, the axis should be labeled with the variable, units, and instrument uncertainty. Number 5, the data points should be clear. Number 6, huh? Number 6, error bars represent the uncertainty range, the 公字. Number 7, error bars should be shown correctly using a straight edge. Straight edge. This is the error bars or uncertainty for your independent variable. Sometimes your dependent variable also have error bars where you're gonna draw it horizontally. Okay? Number 8, data points average only, okay, average value only, should not be connected dot to dot fashion. A line of best fit should be drawn instead, a smooth curve or straight line. The best fit line is not necessarily the straight line. See, that's the thing I'm talking about. A best fit line is not necessarily a straight line. Sometimes a curved line can also be called a best fit line, even though it's a curve, okay? And should pass through all of the crosses created by the arrow bars. Approximately the same number of data points should above a line and below it. If all of the data points are above your line, then possibly you're gonna have a what error? Systematic error. Or if all of the data points are below your best fit line, then you're most likely to have also a systematic error. So that's the reason why when we draw the best fit line, we should make sure that approximately there is the same number of data points above and below your best fit line, so that it fluctuates about your best fit line. Clear? Okay. And number 9, each point that does not fit with the best fit line should be identified. If you have an outlier, leave it as it is. Discuss it and draw a second graph without the outlier and discuss it again. That's how you deal with the outlier. Okay? If you have an outlier. Number 10, think about whether the origin should be included in your graph. What is the physical significance of that point, of that origin? Do not assume that the line should pass the origin. Do not assume. Just say that if you have an intercept, that your line does not pass through the origin, it may suggest that there is systematic error, or the intercept actually represents some physical quantities. Okay? Any questions? Good. So, in principle, the size of the error bar should be well different, should well be different for every single point, and so they have their individual workout. In practice, it would often take too much time and add too much time to add all the correct error bars, and so some or all of the following shortcuts could be considered. 1. Rather than working out error bars for each point, use the worst value and assume that all other error bars are the same. So basically, if you use the worst one, then the other one cannot be worse than this because it's already the worst. So it's pretty safe to pick the worst error bar, the largest error bar, and apply them to all. Does that make sense? Okay. So in the report, include the explanation. Okay, you need to explain why you do that. Explanation is like taking the highest uncertainty, we are responsibly sure that the result is blah blah blah. Okay. Number 2, you should discuss the experiment results at the end of the lab report. What type of dependence you discovered. For example, when graphing experiment data, you can see that immediately if you are dealing with random or systematic error, if you can compare with the theoretical or expected results. For example, if we are investigating the relationship between, let's say, just that example, period equal to 2 times root m over k. then we should expect that t squared should be proportional with m, right? So it should be a straight line path through origin. But if that's your theory, right? That's your expectation. But if your result is not matching with that, you need to compare. Compare the experimented results or the theoretical one. What could be the thing that what could be the factors that makes the difference between the theoretical expectations and the actual results? Any questions for me? Okay. For example here, the dots are the predicted result, or the perfect results. The X are the random errors, and the triangle are systematic errors. What are the triangle systematic errors? Because all of them are constantly above the perfect results. The random errors because it's fluctuate up and down, which fits the real world data collection. Okay? Alright. Lastly, what are the max and minimum lines and what to do with them? In DP, we also requires you, when you have the best fit line, we also require you to draw the worst fit line. What is worst fit line? So, remember that most physics experiments leads to graphical analysis of data, and we can use graphs to express and find uncertainties. You must include graphs of your data, and let's say if you find the best fit line, the slope of that line after linearization, and therefore you have find the value of the slope that corresponds to some physical quantity. That's an example. Now, you must use the maximum and minimum best fit line. Or sometimes, in the question, you might see it, quote, quote, as a worst fit line. Basically, referring to the maximum slope and minimum slope that still pass through all of your arrow bars. To determine the final uncertainty in the stated value of the slope of your best fit line, and here's how. So, you will have a graph like that, okay? Let me redraw this, because this could be a bit messy. So, for the simplicity, I'll just use 3 data points. So, our best fit line could be this one here. Now, what about this is a medium slope. What could be the possible largest, greatest slope that you can draw that still passes all the error bars? So maybe you want to start from here and end at somewhere maybe here, right? So if you connect, but you still need to make sure that the straight line is going to pass through the error bars of the middle point. So if you do something like that, oops, it does not pass through this one, so you need to be a little bit more, yeah, maybe the second green line, not that steep one. And then you have a most, I'll just use the black line. So maybe somewhere here and somewhere here. So you draw another line like that. Right? So this is the steepest, which is what we call the maximum, and this is the minimum slope. Maximum slope, minimum slope. Does that make sense? Any questions? Did you guys learn this in math? No? Okay, good. So that means I'm not wasting your time or my time. That's something new, right? Did you learn this in the video on YouTube?
老师说为什么是反过来的动作？
哪里反过来？
是那个是那个是哪里？
Deepest green.
Of intersect. 这个是 maximum value of intercept, not the slope. It's okay, it's okay, it's okay. Right? You should ask question when you're confused, okay? Because it's best to solve it now rather than it confuse you for the rest of your life. Right? Any other thing? No? Is this something useful for you? That you did not learn in the YouTube that I asked you to watch? Great, nice. Okay. So, sorry. So number one, draw a straight line with the least slope possible, which is the minimum best fit line that connects corners of your first and last error bars. Number two, draw a straight line with the greatest slope possible, maximum best fit line that connects corners of the first and last error bars. And determine the slopes of y-intercepts of those two lines. That's going to be your maximum intercepts and minimum values of intercepts. And so for your intercepts, for the uncertainty of the slope, we still use maximum, the steepest slope, minus the minimum slope divided by 2 to calculate it. And for the uncertainty of the y-intercept, what do you think? How can we find the uncertainty of the y-intercept?
Draw another graph.
We already have one graph. Ooh, no, don't show it! Okay.
The maximum
see it?
value intercept and
Yeah, what?
maximum value intercept.
Okay. So we use the maximum intercept minus the minimum intercept divided by 2 still. So you don't need to draw a whole new graph. Why? Because this graph tells you everything. This one has the maximum slope, right? Maximum slope. This one has minimum slope. Isn't here the maximum intercept? Isn't here the minimum intercept? You just need to read the values on your y-axis. And then use this formula to figure out the y-intercept, the absolute uncertainty of the y-intercept. Very clear? Okay. So, very good. Very good. Some visual help. So lines of best fit or maximum minimum line for graph of quantity versus quantity A versus quantity B. Know that by using this technique, you may get max and minimum lines that do not go through all the error bars of every data point. This is okay, you will not be penalized for it, but even so, like, if you can do a little bit better, just do a little bit better, okay? All right. So, let's look at one of the example questions, and let me ask Thomas.
C.
Which one of the following shows the best line for the plotted points? C. So this one here.
Wait. Are they all straight lines?
No. The option should be the C.
What's the requirement for best fit line? Does best fit line need to pass through all the data points? But does it need to pass through all the error bars? What should be the answer?
Or close to around.
What should be the answer?
straight.
A 的部分。
Best of luck. It's not to always be a straight line.
One of the one
Keep it close to the arrow.
one the air.
Okay, let's see. First of all, looking for the line to lie within all horizontal and vertical arrow bars. Then that can eliminate, see? So we have horizontal error bars. Horizontal error bars, okay? A, why is A not correct? It does not pass through the horizontal error bar of this one. This here, both of them, horizontal vertical did not pass through. This horizontal did not pass through. So only graph B satisfies this requirement. Any questions? Okay. All right. Now IB has a requirement that when you conduct an experiment of your own design, you must have 5 levels or variations in your independent variable. We start this from MIP, so you guys are pretty familiar with it, right? 5 levels, and for each level, each variation of your independent variable, you must conduct 5 trials to gather the values of dependent variable. Well, in MIP, we only require you for 3 trials, but it's best to have 5 trials as well. Okay? The 5 values for each dependent variable will then be averaged, and this is an example. Oops. This is an example of a student work. This is a well-designed table containing all of the information and data points required by IB. Now, this table has a title, Distance between magnet and compass needed to change direction of the compass needle versus the time of the magnet spent in the freezer measurements. So, time in the freezer, first of all, your name for the independent variable is time in the freezer. With the uncertainty plus minus 0.2 second, 0, 10, 20, 30, and 40. However, a small thing, plus minus 0.2. Level of preciseness should match. Alright? Okay. Distance between the magnets for dV, IV. With uncertainty, 0.05. And the trials here. So, although the digital stopwatch went to the 100th decimal place, the uncertainty is still much greater because there's no way to ensure that the time of the magnets was in freezer was exact. That's first of all. And second of all, more reasonable uncertainty would be 2 seconds. Uncertainty in opening and closing the door, taking out the magnet, and also reaction time. Each measurement of the distance has instrument uncertainty 1/2 of the smallest increment on the meter stick. So plus minus 0.05 for each single individual. Okay. But for distance measuring, if you use 0.1, it's still okay. Why? because you take two measurements, right? Okay, so the dependent variable, independent variable, 5 tiles for independent variables. Now, the process the data table is here. First of all, you still have the time. You still have the title. Measurement uncertainty in distance was calculated in as range over 2, which has a comment below here to show how the student is going to calculate the uncertainty. Okay. So here's the thing. Usually we see uncertainty is included in the heading, right? What does that mean? That means this uncertainty applies to all the data sets here. But why is here not uncertainty here?
Yeah.
Right? If they have their own individual uncertainty, then you cannot do this. Because if you put the heading, then that means the whole column here applies the same uncertainty. But if they have their own individual uncertainty, you put their own individual uncertainty with them. Okay? Then it's good to have a percentage error here to show how large the error is. And also here, the value of the best estimate must be expressed to the same precision as the uncertainty. And uncertainty has 1 significant figures. Okay, so finally, this guy draw a graph with the arrow bars. And so the size of the vertical arrow bars in the graph is 0.3, which is the maximum measurement uncertainty, and up and down at each point in the graph. The size of the horizontal arrow bars are the instrument uncertainty 0.2 seconds. You need to explain where are those arrow bars coming from. What's the source of the arrow bars? Right, and for the graph, you have the title, the name of the variables, units, scales, equations, specified line, error bars. And then you draw the worst fit line. Make sense? And then you will have the intercepts, maximal intercept, minimum y-intercept. Then you can get that equation for them. Now you can calculate the uncertainty in the slope and the uncertainty in the y-intercept using those two equations. So you're gonna get, that means, okay, maybe your data collected somewhere probably went wrong, right? According to the calculation. So that's a full walkthrough of how to collect data, how to deal with your data, how to get a data table down, how to draw a graph, what is required in all of those details, a detailed walkthrough example here for your physics IA. I hope this is helpful. Okay, any questions for me?
For the systematic error, isn't like the best fit line based on the measured points? So shouldn't it be like you can't get the best fit line like above or below all the values?
When you do it, yes. But if the question, when you have a question in an exam that they deliberately draw it, then you know it's a systematic error.
Oh.
But when you do it, of course, when you draw the best fit line, you won't deliberately draw the best line so that all the data points are above or all the data points are below. Does it make sense? All right, that's everything. But hold on, homework.
啊？这是要爬起来。
才2张纸，别慌。
是 first student factor。我今天的。
哦。 桌子还给我。
你就来我没跳了。你全部学
No.
是一考。
Okay. I will collect homework on our next week first period. Okay.
对啊，我只有4节。